Hi everyone, in this third video of the series, A Beginner's Guide to Hardware Software Co-Design, building a Linux controlled hardware accelerator on the Zynq UltraScale Plus SoC, we're going to be working with Vitis. Vitis is AMD's unified software development environment. It's an IDE designed for developing, debugging, and profiling applications for AMD platforms. It understands the hardware we designed in Vivado. In fact, it uses our XSA file. It simplifies cross-compilation, writing code on our PC that will be compiled to run on the ARM processor on our Zynq board. It provides powerful remote debugging tools, allowing us to set breakpoints and inspect memory on the live target. Throughout this video, we're going to create a platform project. We'll start by telling Vitis about our specific hardware platform using the XSA file from the last video. We're going to create an application project by beginning with a Hello World template to get our project structure set up. Then we'll modify the code by adding the logic to write and read from our half adders memory mapped registers. And finally, we'll deploy and verify our application by compiling and running it on the board, confirming that our software can send two numbers to the FPGA and get the correct sum back. So let's open up Vitis and start working on it. As you can see, I'm using Vitis Unified IDE 2025.1. When it opens, we'll click Set Workspace and create a new folder for our project. So in this case, we'll name it codesign_Vitis and hit select folder. When the new workspace has loaded, we'll go ahead and click Create Platform Component. Here we can just verify that the component location is correct. In fact, it's in our co-design Vitis folder. We'll just leave the name platform there. Hit next. We now browse for our XSA file that we previously generated in Vivado. So we go to the co-design Vivado folder and double click on the XSA file that we modified. And then hit next. We wait a few seconds for the details to load. Once the details have loaded, we make sure it says standalone PSU Cortex A530. This is going to run on the first A53 processor on the Zynq chip, and the architecture is going to be 64-bit. If we open up the Generate Boot Artifact section, we'll see that the PSU Cortex A530 processor has been selected, and then we hit Next. We confirm and finish. This is going to take a few minutes. Now that Vitis finished creating the platform, we'll go ahead and click Build. After the platform has been built or generated, we'll go ahead and create a Hello World example. In order to do that, we go to File, New Example, and then select the Hello World example. Here we click Create Application Component from Template. We leave the default name and hit Next. Then we select the platform that we just created, or that we just built, and hit Next. Then we hit next and finish. When Vitis finishes creating our Hello World application, we can open it by double-clicking our helloworld.c file within the sources src folder. And in this file, we can see the basic Hello World application. By creating this Hello World example application, we can prepare the system for a slightly more complex application. More specifically, it will save us time importing other libraries, such as the platform and the Zynq libraries. At this point, we can go to my repository for this project on GitHub and open the folder Codesign Vitis, then Hello World, src, and helloworld.c. Here we'll just copy the raw content of the file and select the whole content of helloworld.c and paste, thereby replacing the previous content, and then save the file. In this new file, we can see that we load a set of libraries and then start by defining our hardware settings, more specifically the base address of our IP, and then the offsets after this address in which our operands and our sum or result will be located. I will show you in a bit where I got this base address for IP, but in the meantime, the main function starts with initiating the platform, creating a variable for operand A and assigning it the value of 37, doing the same for operand B and a value of 11, and creating a variable for the result of the sum. Then we start printing the values of operand A and operand B and the result of the sum. Then we check if the hardware result is the same as the software result and print the respective result. Afterwards, we clean up the platform and return 0. At this point, we'll just plug in our board. Then we'll set the boot switch to JTAG and power on. We'll build the application, save this preference in our workspace. Then, with our board connected to the computer and to the external power source, the boot switch set to JTAG and the USB power switch set to on, we can click Run. We know that the programming process has completed on the board because the Done LED is on. However, none of the LEDs that should be displaying the result is active, and in fact they should be, because 37 plus 11 is 48, and this is completely within the range of the lower 8 bits of the 32-bit result. So we're now going to open PuTTY and see what the software output is. Within PuTTY, I'm just going to load the settings I previously stored for this board. In my case, I'm connecting to COM3. The speed is 115,200 And if you go to the serial settings, you can see this further detailed. We're using 8 data bits, 1 stop bit, no parity and no flow control. So if we return to the session setting, we can click open. And at this point we have to rerun the Vitis application. So we get this error, invalid target, use connect command to the hardware server. So I'm going to press the POR button to reset the board. And I'm going to hit run again. And we can see that we get this output. We wrote 37 to operand A, we wrote 11 to operand B, we read 48 from the sum register, and in fact this is correct. The hardware result is correct. However, as I previously mentioned, the LEDs that are LD7 through LD0 aren't lighting up. So that means that there is an error within Vivado. Now we'll open Vivado and let's see what's going on. So we open our project on Co-Design Vivado. Once Vivado opens our project, we'll just go to the block design. And here you'll notice that I added a sum port. The problem was that I didn't create this port previously. So to show you how I did this, I'm just going to delete this port. And again, I'm going to right click on the sum and hit create port. I'm just going to leave the port name as sum. You can see how the direction automatically is set to output, that it's going to create a vector from 31 to 0, and it's going to connect to the sum selected pin. So we'll hit OK, and we can see our 32-bit output bus. At this point we'll hit run synthesis, and once it completes we can open the synthesized design. We'll get several critical warning messages related to the fact that we haven't assigned package pins to all ports, but we can ignore these messages because we know they're due to the fact that the sum output bus has 32 bits while we only have 8 LEDs, and therefore there will be 24 bits without any pins assigned. So we'll hit OK. We can expand the sum port and we'll see that the bottom 8 bits have already been assigned a pin, which we did in the previous video. At this point we can run the implementation, generate the bit stream, and proceed to export the architecture as we did in the previous video. Modify the XSA file with a tool like 7-zip, and then we can pick up where we left off in Vitis. As you'll notice, if you expand the platform, the settings, and double click on Vitis comp.json, you'll see this button, switch reread XSA. I have tried replacing the XSA file from here and building the platform, but unfortunately in my attempts it doesn't pick up the platform correctly. So what I've done is I just delete this project and start from scratch in Vitis. If you want to save some time, you can just extract this hello world.c file since it's the only one we modified, and then proceed from the beginning of this video. Once you've reloaded the platform and created an example hello world application and replaced its content with the one in the repository, we can again return to this file, to the hello world.c file. As I mentioned earlier in this video, we have this base address for our IP, and I wanted to show you where I got it from. So if we return to Vivado and go to our block design, we'll notice that there's an address editor tab, and we'll take the master base address and place it in our Vitis file. The register offsets come from our Axie4 peripheral definition, and we basically stated that each of these registers would be 32 bits wide, which translates to 4 bytes, and that's why we start at 0, then the second operand or operand B starts at byte 4, and the offset starts at byte 8. At this point, we can build our application and run it on our board, and this time we'll notice that LD4 and LD5, or LED4 and LED5, are both on. This to reflect the binary value of 48.